This lecture, we will see in detail the construction of angular momentum matrices using a Clebsch Gordon coefficient. Before going into the detail, we will see about the matrices spin off particle. This we have seen elaborately in my lecture Pauli spin matrices, and I have derived Pauli spin matrices also. So I don't want to repeat here. Just I want to highlight one important point. As I am saying always, that spin angular matrices are orbital angular matrices or total angular matrices. That is uh, S matrix, L matrix, and J matrix all comes under Lie group. That means all the properties are the same for the Lie group. So, in my lecture about polyspin matrices, I have derived that Sx, Sy, Sz, and S squared. Same thing is valid here also because J also comes under Lie group. That is whatever property valid for polyspin matrices valid here. There we have seen Sx, Sy, Sz, and S squared. Same matrices I have given it here because properties are same for Lie group. So only thing is I have changed the symbol S by J. That's all. So you can refer my earlier lecture. Now we will construct the angular momentum matrices when J is equal to 1. In the case of polyspin matrix, J value is equal to half, so we will have 2J plus 1 element, matrix element, 2J. There J is half, so this will be 1 plus 1. Uh, so it will form a 2 by 2 matrix. Poly matrices will form 2 by 2 matrices. Here, since J is equal to 1, this will form a 3 by 3 matrices. 2J, 2 into 1, 2 plus 1, 3. So 3 by 3 matrices. You know very well that this m value for j equal to 1, m changes from 1 to minus 1 in step up 1. So 1 minus 1, 1, 0, minus 1. You will have, it will vary from plus j to minus j. M value varies from plus j to minus j. So this is Jm bracket vector. Here, you know the bra vector is a row vector. That is, you can see bra vector. First row is 1, 1, 1, 1, 1, 1. So all are bra vectors. Here J is 1. Of course, we have taken J is 1 only. So M is 1. M will take value 1, then 0. 0, M value 0 I have taken in the second row. M value minus 1, third row. See, I have shown all in red color. All pra vector correspond to row vector. Since M is having 3 value, 1, 0, minus 1, we have 3 rows. Similarly, about the column vector. So the get vectors are, you know very well, is a column vector. Here this is in the first column you will have 1 1 m equal to 1, and the second column m equal to 0, the third column m equal to minus 1, which I have shown in green color. I have shown the green color the get vector, that is column vector, and in red color the row vector, which is the pra vector. Now what will happen when operator j squared act on this vector, this get vector? So I have introduced j squared all in all the element. So 1 1 j squared 1 1 1 1 j squared 1 0 likewise. So I have introduced to the operator j squared here. When j squared act on the get vector, you will get the eigenvalue of j into j plus 1 h cross square. Like in the case of L, it is L into L plus 1 h cross square. Same is the case for total angular momentum. So you know the eigenvalue and with the get vector. Here, it is important to note that the operator j squared, that is square of the total angular momentum operator, does not change the state. Here also it is Jm, here also it is Jm. So, as I said just now, I have introduced J squared in the Dirac, matrix form. So, all vector, first rows, second, 1 1 is a bra vector in the first row, 1 0 is bra vector in second row, 1 minus 1 is a bra vector in third row. Similarly, the get vector. Here, you have to remember that the J square operator does not change the state. So, it will become 1 only when bra vector and get vector are the same. So, that is only for diagonal matrix. Here you can see bra vector also 1 1, get vector also 1 1, 1 0 1 0, 1, 1 minus 1 1 minus 1. All are different. See, this is different, bracket vector different. Here also bracket vector difference. Here also bracket vector difference. Here also. Similarly, here also. So only diagonal element exists. So when j equal to 1, 1 into 1 plus 1, 2. So this will become 2h cross squared. I have taken out the eigenvalue of 2h cross squared outside. So only the diagonal element exists. So this will be 1. So j squared is equal to 2h cross squared. This unit matrix, that is it. 1 0 0 0 1 0 0 0 1. So this is about J squared matrix, which is very simplest case. Now, next simplest matrix is JZ matrix. We will see the JZ matrix for J equal to 1. When JZ act on get vector Jm, you will get the eigenvalue of mh cross. And here also you remember that you have to keep it in your mind that there is no change in state. That is Jm does not change. Jm get vector Jm is as Jm only. So instead of J square, now I have replaced Jz as an operator. Here, since there is no change in the state of the get vector, you can see only the diagonal element exists. Because here 1 1 1 1 1 0 1 0 1 minus 1 1 minus 1, which I have shown in red color. Other things are bra vector and get vectors are different in all other cases. Bra vector and get vectors are different. So only the diagonal element exists. First, see the first row, first column, the diagonal element, m is here 1. So h cross I have taken out. So m is equal to 1. In second case, m is equal to 0. So I have put 0 here. In third case, m is equal to minus 1. So the JZ matrix is equal to h cross 1 0 0, then 0 0 0 0 0 minus 1. So this is about JZ matrix. Now our next task is we have to find the JX matrix and the JY matrix. You know the rising operator J plus is equal to JX plus IJY. Similarly, the lowering operator is equal to Jx minus Jij. That means if you add these two, J plus j minus. So this second term I jy will cancel with this minus I jy. So you will get to jx plus jx, that is 2jx. That means jx is equal to 1 over 2 j plus j minus. Similarly, you subtract j plus with minus minus. So you are subtracting these two. If you subtract these two, x will go away. You will get ijy minus of minus I will become plus ijy. So you will get 2 ijy. That means jy is equal to 1 over 2 I j plus minus j minus. So now our task is we have to find the j plus matrix and j minus matrix. Now we will find the j plus matrix. That is j plus means rising operator. So when rising operator operate on get jm, you will get the uh, eigenvalue of j into j plus 1 h cross squared minus m into m plus 1 h cross squared. This we have designated as Clebsch Gordan coefficient. And also in my and here I would like to highlight two important point. When j plus operator act on this get vector jm, it traces the state m by 1. That is m will become m plus 1. It will not change the state of j. That is one important point. Another important point is in my previous class Clebsch Gordan coefficient, I have explained that you have a stretched state. That is the lowering operator operate m changes from plus j to minus j. You cannot go beyond plus m and you cannot go below minus m. That we have seen in my previous class Clebsch Gordan coefficient. So it cannot m cannot go above plus j or below minus j. Uh, so you can apply what here you can see from this expression itself. When m equal to j, this will become j into j plus 1 h cross squared minus j into j plus 1 h cross squared. So this will get cancelled. It will become 0. Now what I am doing is, see here one h cross squared, here one h cross square. I am taking this h cross squared outside, which will become just h cross. So and also this j into j plus 1. Since j is 1, 1 into 1 plus 1, 2. So this will be 2. So I can write this as h cross square root of 2 minus m into m plus 1. Of course, you have this j m plus 1. Uh, Now, as I said, when j is equal to m, this will become 0. That is, this coefficient will become 0. You cannot go above j. Uh, when j is equal to m equal to j, it will become 0. You can see the first column where 1 1 1 1 1. So jm, this is jm, where m is 1. So you cannot go above j. M cannot go above j. So this will become 0 due to its physical property, as well as using this expression. You can see it will become 0. So first column will become 0. Now I am operating with j plus for other yeah, element, other six matrix element. We will see what will happen to this. In the case of rising operator, when rising operator act on Jm, just now we have seen, it will become h cross square root of 2 minus m into m plus 1 and this get vector m plus 1 here. That you have to keep it in your mind. So here you can carefully watch this matrix element. When j plus act on 1 0, what will happen? This 0th state will become 1. M will become 1 because it will raise the level of M by 1. So here 1 1, here also 1 1. So this matrix element exists. What about this? When rising operator act on this M, because rising up operator and lowering operator will uh, affect only the M, change the state of M, not the J. So when it act on minus 1, so this will become 0. So bra and get vectors are different. Here also same is the case. This will become 1 1. Here you have 1 0. Similarly, this when you raise this level, 0 will become 1. Here minus 1. Same is the case with already there is minus 1. When you act it act on j plus, it will become 0. So only these two components exist after rising operator act on this get vector. This will become 1 1. So 1 1 inner product of 1 1 with 1 1 is 1 due to orthonormal property. So only these two other element will become 0. So these two element here you can see, since the inner product is 1, uh, m, m equal to, here you can see 1 0. Here m is 0, so this will become 0. Here in the other case m is minus 1, so this will become 0. So only square root exists. So you will get the square root in the first row, second column, and second row, third column. You will get the square root of 2. And I have taken h cross outside. Now we will see the lowering operator j minus. When j minus act on jm, the m state of m will reduce by 1. That is m minus 1. And also here, previous case in the rising operator, we have seen this is m plus 1. Now it is m minus 1. That two difference are there. So as usual, you take h cross squared outside. So it will become just h cross. So since j is 1, so the first term will become 2 minus this m into m minus 1, get j m minus 1. Here you can see I have already explained the m state of m cannot go beyond minus j. That means minus j here is minus 1 because j value is plus 1. Um, uh, minus j minus j is sorry, minus 1 is minus j, so minus j. So m value cannot go below minus j, that means below minus 1. So when this operator act on the mth state, it cannot go below 1 minus 1, so this will become 0. Not only that, if you substitute minus 1 here, what will happen? Minus 1 will become minus 2 here, or minus 1, this will become minus of minus 2 will become plus 2. So here one minus already, one here is plus 2 minus 2, 2 plus 2 minus 2 will become 0. So this third column will become 0. The stat column will become 0. What will happen to other six matrix element, we will see now. So we have seen when lowering operator operate on get jm, you will get h cross square root of 2. This 2 comes because j is equal to 1 minus m into m minus 1. The get j m minus 1. Here one, it reduces one state. Now you see this element. What will happen to this? M is 1, 1 becomes 0. Here it is 1, 1, here 1, 1, 1 0. So naturally orthonormal property, this will become 0. Similarly, what about this? Uh, this 0 m0 will become minus 1. Here 1 1, here 1 minus 1. This also will become 0 due to orthonormal property. Uh, then this one, when j is equal to j minus arctan m, so this will become minus 1. So here 1 0 in your, here 1 0, here 1 minus 1. So this also will go to 0 due to orthonormal property. Here when this act on lowering operator act on this m1, this will become 0. Here 1 minus 1, here 1 0. So this also will go to 0 due to orthonormal property. So only existing term is this one, which I have shown in red color. When lowering operator act on m1, it will become 0. So 1 0 1 0. Similarly here, when j lowering operator act on m, that is here m is 0, so this will become minus 1. Here 1 minus 1, here 1 minus 1. So only these two term exist. So if you apply this value m equal to 1, means 1 minus 1 0, this second term will become 0. Here m equal to 0, so this will become 0. Only h cross square root 2 exists. So I have taken h cross, and square root 2 I kept inside. Square root 2. Here one square root 2, and here square root 2. That is second row, first column, second column, second row. So these two only exist. So j minus is equal to h cross 0 0 square root 2 0 0 0 square root 2 0. Now we will find the Jx matrix. We have seen already Jx is equal to 1 over 2 J plus J minus. This is J plus matrix, and this is J minus matrix. So if you add these two, you will get here also one H cross, here also one H cross. Of H cross, these two element, square root of 2, square root of 2, these two element comes here. Similarly, these two element comes here. Outside there is a 2. So you can take square root 2 outside the matrix. So square root 2 divided by 2 is equal to 1 over square root 2. So h cross uh, over square root 2, this all this element will become 1. So these become 1, and these two become 1. This is the Jx matrix. Similarly, we can find Jy matrix. Already we have seen Jy is equal to 1 over 2i j plus minus j minus. So this matrix minus this one. So here already there is a H cross I have taken out, and 2i, this 2i comes here in the denominator. Then this minus this. So I have made it minus square root 2 minus square root 2. Now what I am going to do is I will multiply and divide by I. So this will become I squared, which is minus 1. In the numerator you have I. Now what I am going to do is I am going to bring this minus I inside the matrices. So this one will become minus I, and this one also will become minus I. This minus 1 will become plus I, and this minus 1 also will become plus I. So Jy matrix is h cross over square root of 2 0 minus I 0 I 0 minus I 0 I 0. So these are the angular momentum matrices. Just now we have derived Jx is equal to h cross over square root of 2 0 1 0 1 0 1 0 1 1 0. Jy is equal to h cross over square root of 2 0 minus I 0 I 0 minus I 0 I 0. Similarly, Jz we have seen h cross into 1 0 0 0 0 0 0 0 minus 1. Similarly, say j squared 2h cross squared, then the diagonal element are 1, all other elements are 0. These are the four matrices we have seen for j is equal to 1. We can similarly find the matrices for j is equal to 3 by 2. J equal to 3 by 2 means 2j plus 1. What will happen to 2j plus 1? You will have a 2j plus 1 into 2j plus 1 matrices. So 2j plus 1 is j. Since j is equal to 3 by 2, you will get 2 into 3 by 2 will become 3 plus 1. 3 plus 1, 4. So in the case of j equal to 3 by 2, you will get 4 by 4 matrix. It will goes on similar. Uh, Similarly, it will goes on. So if j is equal to 2, then you will get 2 to 4 plus 1, 5 into 5 matrix element. It will go like that. So this is the method of constructing angular momentum matrices. Thank you very much for watching my videos and supporting me continuously. Subscribe my YouTube channel. Channel ID is youtube.com/c/vasuvpc. Thank you very much.